Hello everybody, my name is Max Domers. I study aerospace engineering at SDSU. Today we're going to be looking at a strain rosette problem. Over here is a diagram of our three strain gauges, and this is what a strain rosette is. It is three strain gauges. Alright, here is the workflow for the problem. We're going to start off with our data that we get from these three gauges here. We're going to have to transform them into x and y and also gamma. We do this using the strain rosette equations, which I put up here, equation 1, 2, and 3. After we get x, y, and z, or x, y, and gamma, then we get to have a state of strain. From there, we have two ways we can go. We can either go to Mohr's circle, and this will give us our principal strains, or we can go to a state of stress, because stress and strain are related by Hooke's law. I prefer going the left path because when you go the right path, you have to remember to divide the y-axis by 2. All right, for our question here, it says that we have a 75-degree angle here, a 75-degree angle here, and gauge number 2 has 0-degree angles. We got to make sure to measure it from the x-axis. Counterclockwise is positive and clockwise is negative. All right, gauge 1 reads 150 times 10 to the 6 inches per inch. Gauge 2 reads 400 times 10 to the negative 6 inches per inch. And gauge 3 reads 250 times 10 to the negative 6 inches per inch. All right, it also specifies that we're going to be working with 661 T6 alloy aluminum. I already have the constants up here. E is the modulus of elasticity, G is the modulus of rigidity, and V is Poisson's ratio. All right, the whole question's on there now. So we get to take these values here and transform them into these stresses here, and we're going to use these stresses to solve for stress in the x direction, stress in the y direction, and gamma xy. First, let's say this is going to be stress A, stress B, stress C. 1, 2, 3. All right. From here, we get to say stress A is equal to 150 times 10 to the negative 6 inches per inch. Stress, and it's going to be at a negative 75-degree angle. It's negative because we're looking downwards. Stress B is going to be right in the middle here. It's going to be gauge number 2. And for this one, we have 400 times 10 to the negative 6 inches per inch. Now we have stress C at 0 degrees. And stress C is going to be this number 3 gauge here. 250 times 10 to the negative 6 inches per inch. And this one's going to be at positive 75 degrees. All right. Now, you may notice we're going to be using these equations here. If you look at the workflow, you're going to be using strain rosette equations, which are these ones up here. And we have epsilon A, epsilon B, epsilon C, and we have theta A, theta B, and theta C. The order that you choose the gauges in don't really matter. You might notice that all these equations are almost the exact same. They only have theta switched out. So the order doesn't really matter for which you choose them for. All right. So now you may notice that we have one unknown here, 2 unknowns here, 3 unknowns here. We have 3 equations and 3 unknowns. What this means is we can plug them in and solve for epsilon x, epsilon y, and gamma xy. All right. I have my work here. It's pretty tedious and it's just algebra and moving things around. So I'll put that at the end of the video. But I already solved for them. But let's plug them in first. All right. For question number 1, we can get rid of some of this stuff. Oh God. Never mind. All right. This one is, I'm plugging in question number 1. I misspoke. I mean equation number 1, this one up here. Epsilon A, which is right here, 150 times 10 to the negative 6 inches per inch is equal to epsilon x cosine 2 theta A. Theta A is negative 75. I put all the cosine angles up here, so we get to look at this. Cosine squared of negative 75 is cosine squared of negative 75 degrees is equal to 0.067. Plus epsilon y. Sine squared of negative 75 degrees is equal to 0.933. And then we get to add that to gamma xy, which is going to be multiplied by cosine of negative 75 times sine of negative 75, which I put over here. Sine of negative 75 times cosine of negative 75 is equal to negative 0.25. All right, that's going to be our first equation. Our second equation, this one's going to be much easier because you may notice that it's in the x-axis, which means all the strain is going to be already acting in the x-axis. But if you didn't understand that, you could still solve for it. Theta is going to be 0 here, which sine of 0 is equal to 0. This component gets wiped out. Sine of 0 here is equal to 0. This component gets wiped out. Cosine of 0 is equal to 1. So we're left with strain B is equal to strain X, which is equal to 400 times 10 to the negative 6 inches per inch. Strain B is equal to strain X, which is equal to 400 times 10 to the negative 6 inches per inch. All right. Lastly, we have strain in the C direction, which you may remember we said C direction's gauge 3 right here. Equation 3 is going to be epsilon C, which is equal to 250 times 10 to the negative 6 inches per inch, which is equal to epsilon x cosine squared x cosine squared of positive 75 degrees is going to be the same as cosine squared of negative 75 degrees, which is 0.067. Plus epsilon y of sine squared of 75 degrees, which is equal to 0.933, plus gamma xy of sine theta, cosine theta, theta is equal to 75, and that's going to be positive 0.25. All right, our variables are now plugged into our 3 equations. We have 3 equations, 3 unknowns. That means we could solve with system of equations. All right, this is pretty tedious. I already did it. I used Wolfram Alpha. You can plug this into your computer or calculator, and it does it for you automatically. But if you wanted to solve for it, what you need to do is, this one's already solved for, epsilon x is equal to 400. You need to isolate epsilon y, or you can isolate gamma xy, and then whichever one you isolated, you get to plug into the next equation, because we have 2 unknowns, 2 equations, and then solve for that. And for my answers, I got all right, epsilon x is equal to 1 over 250 1000 epsilon y is equal to 2.487 times 10 to the -5, and then gamma xy is equal to 8 times 10 to the -4. These are all strains, which means they're going to be in inches per inch, except for the last one, because this one's measured in radians. Gamma is kind of the tilt of it. All right. Now that we have x, y, and gamma, we can erase these equations and give ourselves some more space. All right. Now, if we look back at our workflow, we use the rosette strain equations. We have a state of strain. Our known state of strain is shown right here. And we have our two options like I talked about earlier. Now we're going to use generalized Hooke's law, which I put the equations right up here. Equation number 4, 5, and 6. Actually, let's erase a little more. All right. This one's on equation number 4. We're using equation number 4 here. Stress in the x direction is equal to the modulus of elasticity, E, right here. I'll just put E for now, divided by 1 minus Poisson's ratio squared, times epsilon x, which we solved for, which is 1/2500, plus V, which let's plug in for now, which is 0.33 epsilon y, and that is going to be 2.487 times 10 to the -5. All right. One more here. All right. Let's switch this E out for 10.1 times 10 to the 6 psi, pounds per square inch, and then might as well switch this one out to 0.33. All right. These are all numbers, so you can plug that into your calculator. And for your stress, you will receive the number, stress of x is equal to 4,626.27 psi, and we want this in KSI because it's specified in the question. So let's switch this over to KSI. To switch to KSI, there's 1,000 KSI, sorry, 1,000 PSI per 1 KSI. So we can divide this by 1,000. Move the decimal place over here, and we get 4.627 KSI. All right, this is an important number. We're gonna need this later. Sigma y will be equal to, this first part's gonna stay the same, so might as well do this. Sorry. All right. 0.1 times 10 to the 6 pounds per square inch divided by 1 minus 0.33 squared times, now this is going to be e to the y, since we're using equation number 5 here. Strain in the y direction is going to be equal to 2.487 times 10 to the -5 inches per inch. And then look back up here, Poisson's ratio, which is 0.33 times e to the x, which is 1/2500. All right. These are all numbers. You put that into your calculator, and you will receive the number 1,778 psi, which is equal to 1.778 KSI, which is equal to the stress in the y direction. All right, 2 important numbers. Let's box these. These are very important. All right, and the last one is very easy. Tau xy is equal to modulus of rigidity times gamma xy. So to do this one, tau xy is equal to g, which I put up here, 3.7 times 10 to the 6 psi. 3.7 times 10 to the 6 psi times gamma, which we solve for, and that is 8 times 10 to the negative 4 radians. All right, this simplifies to be 2.96 ksi, and then now we have a known state of strain, which is good because now we could use Mohr's circle to find the principal stresses. All right, let's take these important numbers and move them somewhere over here. Sigma x is equal to 4.627 ksi. Sigma y is equal to 1.778 ksi. Tau xy is equal to 2.96 ksi. All right, now we are very close to being done. Right now, we're on this step, the state of stress. So now we need to use Mohr's circle to get principal stresses, which is a fancy way of saying where is the stress the strongest and what is its maximum value, where is the minimum value, and where is the maximum shear stress too. All right, these are our values right here. What we want to do is we want to plot sigma x with negative tau xy, and we want to plot sigma y with positive tau xy. We get up to 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. All right. Like I said, positive 4.627. 1, 2, 3, 4.627, which is right here. And then move down by negative tau xy, which is about 3. That's going to be this point. Let's label it here. This is 4.627 comma negative 2.96, and all this is in KSI. All right, our next one's going to be positive stress y and positive shear. Positive stress in the y direction is going to be almost 2. It's going to be 1.77, which is going to be right here. And that's going to move up to 3, just about 3, right under 3. Right here. Now we're going to take these two dots and we will connect them. And then this number right here is going to be our average strain, which we can find, our average stress, which is stress average, which is very easy to find. What you do is you take these two stresses and add them and then divide them by 2. 4.627 plus 1.778 divided by 2. We get our average stress is 3.2, which is right about where we have it. 3.2. 3.202. So let's just leave it at 3.2. All right, and now we have a diameter of a circle, which means Pythagorean's theorem can be used to find the radius here. Straight up and down is gonna be, I should have labeled this point. This is 1.778 comma 2.96. In the x direction, it will be this radius here, which is 3.2, minus this area right here, which is 1.778. And the change in x will be 3.2 minus 1.778 is 1.422. So that's just going to be this bottom side of the triangle. The top part is easy, it's just going to be 2.976. And then using Pythagoras' theorem, we get to square both of them and then add them to each other. 2.976 squared, and then take the square root of both of them. And that's going to give us what should be a radius, which looks to be about 3.3. Let's call that 3.3 because it rounds very close. 3.3. All right. Radius is equal to 3.3. Now things get very interesting because we can now find our principal stresses very easily. 3.3 straight up will give us our maximum shear force. Our maximum tau will be 3.3 in the y direction. So let's call it 3.2 comma 3.3. And this is going to be our maximum shear. Tau max is equal to 3.3 plus or minus. Since it's centered, it's always going to be centered in the middle because that's just the nature of shear. It is positive and negative, both in different directions, are always going to be equal. So positive 3.3 is our shear max, negative 3.3 is our shear minimum. All right, 1, 2, 3.3, right here. All right, and now for our other ones, we get to add 3.3 plus 3.2, which will give us 3.5. Sorry, 6.5. 1, 2, 3, 4, 5, 6.5. This will be stress number 1, also known as our maximum stress. And 3.2 minus 3.3 will be negative 0.1, which is right here. Now we could just draw a nice little circle. And here we go. Shear 1 is equal to 6.5. Shear 2 is equal to negative 0.1. And this is going to be in KSI, KSI, KSI. Tau and shear. And then these are our principal stresses. Now let's reread the question one more time. All right, answers are in KSI, which is how it should be. We use Mohr circle, which is what we should have done. And we found sigma 1, sigma 2, and tau max, which means we're done with this equation. Thank you all for your time. I hope you enjoyed my video.